Yeah, welcome to the CERIAS seminar for March 20th, 2019. Today we have with us Dr. Satish Kumar, who comes to us from Coastal Carolina University. He does a lot of work in security of mobile devices, Internet of Things, also works with machine learning, has a wide variety of interests that tie in with things that we do in CERIAS. We can almost claim he has Indiana roots. He did his education, his graduate work was done just across the river in Louisville. But then he headed east rather than coming north and west, so we had to bring him back here. So welcome to Dr. Kumar.
Hi everyone. It's a great pleasure to be here and give a talk on cybersecurity in this CERIAS seminar. So I will go over my work with students on the securing IoT-based cyber physical human systems against diverse attacks. So I will start the talk with the introduction to the problem, the motivation, and the security framework that we have developed to address these attacks, and also some of the experiments that has been done in these areas for cyber physical systems and the IoT simulation attacks. And finally, I will conclude the talk with a summary and the future work directions. So let me start with the introduction and the motivation. So what is cyber physical systems? What is cyber physical systems? Like anybody like?
Involving, so, I mean, I would say systems that involve computers, humans, and the real world.
So cyber aspects and the, yeah, you're right, like cyber aspects, yes.
Would that include things like biometric scanners or eye scanners or things that implement a device that directly interacts with a human physical interface?
Sure. So basically it involves the cyber components as well as the physical components that interacts with the cyber system. But now, like if we involve human systems in that, right? So it becomes more complicated, right? Like human directly interacting with the cyber aspects and the physical aspects. So the concept of Internet of Things is coming up, right? Like, so it kind of like is an enabler to develop these systems, implement these systems, cyber physical systems. And along with Internet of Things and cyber physical system, the dynamic nature of the human, right? Unpredictability nature of the human is very difficult to model and like integrate within the cyber physical systems. So let's look at that with an example here, right? So one of the important cyber physical system that we could see, like in real life, is aviation cyber physical systems, right? So it is very critical system, cyber physical system. So as you could see here, physical system could be like the dynamic, physical dynamic aspects, along with the cyber aspects of, so for example, the cyber aspects could be here, like the communications between the land system and the wireless, like in the space systems, right? And also the softwares that go in between, like activating that like network, the data integrity aspects. And to add to that, right, the human component, right, which kind of where, like for example, the pilots interacting with these controllers, the flight controllers, right? So a lot of controls happening between different components, right? That makes it more complex. And it is very important, critical to make sure there's a safety and security aspects of that, right? So this is a very good example use case scenario for cyber physical human systems. So as you could see, like we all know that safety is a very important aspect of this aviation cyber physical systems, right? And on top of that, security is also very critical here, right? Like because it kind of there's an interlink between the safety and security. And moreover, like so there is the attack space, right? The space is also increasing. The surface area is increasing, right? With so many components interacting, right? And the possibility of attacks are also very high. And on top of that, right, as you could see, like there are multiple opportunities for the attackers, right, to collude, interleave, and attack, right? So that kind of results in very complicated cyber physical systems attacks, right? And the systems kind of behaves in Byzantine fashion. And as a result, the securing that system is very much tougher, right? So interaction between cyber, physical, and human systems in this important aviation systems. So for example, like just in the cyber aspects, right, wireless networks is part of that cyber aspects. There are so many possible attacks are possible here, right? Like for example, you could have like denial of service attacks, could have like the wireless intruders, like misconfiguration of the access points between various levels, phishing attacks. And to add to that, the human aspects, right? So as you could see, like from the 2014 IBM study, that like 95% of the attacks, cybersecurity related threat issues were kind of due to human issues, right? So that human issues could be like from intentional errors, or it could be unintentional errors, it could be like malicious attacks. Somebody could like compromise their identity, right? And like humans' identity, and also like possibility of breach in the privacy, right? So all these are part of this human-related uncertainty. So also there's a lot of research is needed, right? Like to study this dynamic nature of this human involvement in the cyber physical systems, as well as the collaborative attacks that is possible with these human systems, and especially like with bias and all that, like modeling the bias and the tools needed for that. So the motivation for the research is basically like how to like create predictive models, right? Taking into account this dynamic nature of the human involvement, and also like a possibility of having a good integrated intrusion, prevention, detection, and detection framework that can be implemented in an integrated fashion, right? So and also like there's a very high level need of intervention is needed to detect the attacks and respond as soon as possible, right? So that could be need of like vulnerability assessment as well. So to address these issues, this is the framework that we have been developing, is as shown here. So basically, like we could model like IoT based cyber physical systems as different factors, like human factors, the important cyber factors, the attack factors that could help. So once if we can identify some of these factors, right, we could identify the important factors that could be helpful to detect threats, right? Threat index, right? We can do vulnerability assessment and then identify the parameters to detect threat in the system, cyber physical system. So once we calculate the threat index, right, and compare that with a threshold, response and protection action can be taken. to ensure the system gets into the stable manner, stability is achieved. So there's kind of a control loop, right? And it needs to be always activated, right? Like with the threat detection and the response. So like machine learning data mining can be kind of used to identify the parameters, detect the threat, and take action. So it's kind of analogous to like a biological model, right? Like where like virus is detected and an antivirus can be subjected to identify the attack and take action, right? Like based on the body parameters. So we can keep computing threat index over a period of time, and based on like comparing it with the threshold, we can detect the attack and take response actions. So again, so the threat index could be some kind of levels that can be come up with, like 1 to 10. So 1 to 3 is normal level, 3 to 7 is like uncertain level, like 7 to 10 is like vulnerable level, right? Like, or the action needs to be taken immediately. So this could be computed using fuzzy logic or like any other machine learning techniques. And whatever the number that we can come up with, the threat index, that kind of quantifies the vulnerability of the network or a node or the system itself. So the estimation architecture, like threat index estimation architecture, we came up with is as shown here. Like, so basically, like once we identify the parameters, like cyber parameters or physical parameters, human system parameters, we could, for a particular attack, right? So these parameters can be fed into this specification system or component in the architecture, and that the crisp values can be converted to like fuzzified values, fuzzy membership functions, and that can be fed to this inference engine, right? So for example, if you have like 3 parameters with 3 different levels, right? Like normal level, uncertain level, vulnerable level. Like we will have like 3 power 3 rules, and each rule will be used to compute this inference engine for final threat index at a given time t, right? Using this defuzzification model. So finally, like this threat index is the calculated from defuzzification can be used to quantify whether the node or a network or the system is under threat. So this is how the rule strengths and the rule output are being used to calculate this threat index. Like for example, if you have 3 parameters and 3 levels, like there will be like 27 rules, and for each rule, the summation of the weight and the output will be used to calculate the threat index. So for example, here, like if N1 is under attack, like the parameters can be measured, the cyber aspects or physical aspects or human aspects of the parameters at node 1 can be used and fed into the machine learning or fuzzy framework to compute threat index at node N1 to identify whether a node is under attack or not. So once a node is identified, right, whether it is under attack, like the response framework can be subjected to that node, like to the neighboring nodes in that system where the node is under attack, right? And a corrective action can be taken to identify the intruder that causes this attack and isolate from the system. So for example, like if we have like 5 nodes that is near to this node N1 which is under attack, and by measuring the parameters, important parameters that is that can be sourced from the neighboring nodes, we can identify based on the flags and the counters, like identify which node is is the intruder and take response actions, isolate the node or take corrective action for those nodes that are near to this node under attack. So we conducted some simulation experiments for this for the IoT system to identify the parameters for different attacks, right, and calculate TI and take action. So Contiki OS with Kuja simulator was used to simulate threat models, like with IPv6 RPL routing protocol for the loss power and noisy networks. So were used, and we used like so one sync node, right, that kind of gets the information, right, and 25 nodes that sends the information to this sync node, right. So basically like 25 nodes will be sending the packets like every 1 minute, right. So as a result, like for 4 minutes, total 4 minute simulation, like the source sync node will receive 100 packets. So that is the simulation, and that is we had a like 1 minute warm up time in the simulation. Right? After that, this protocol destination oriented direct cyclic graph will be negotiated, and the node is and the system is formed, the network is formed. So we conducted the experiments like for 3 times, like with 3 different random seeds, and so each time the simulation was conducted with like in the 5-minute period, with 25 nodes sending their data to the sync node, a total of 100 packets. And like for the energy consumption, energy usage of these nodes, like so we use this power trace plugin that is included in Contiki to kind of trace the energy usage in this each of these nodes. Right? So so the sync node is doing all the work, right? Like receiving all the packets from all the 25 nodes. So they were kind of working in 100% of the time, whereas like all the collect nodes were only working 1% of the time, right? And the whole network like averaged about like 5% throughput during the simulation. So we implemented several attacks. One of them was the sync hole with selective forwarding attack, right? So the concept of sync hole is basically like, so it kind of attracts the node, malicious node attracts the other nodes, right? Like as if it is the good node that kind of sends the, like that can act as a router, right? So, so by just forwarding these control packets, right, all the other nodes are attracted to this node, and what this malicious node does is like it will not transfer the data packets, right? It will only transfer the control packets. So to implement that, what we've used is, so basically like this malicious node which is 26, kind of advertise that that it can send the control messages, right, to the other nodes. Like whereas 1 is the real control, real sync node, right? So we altered the code to drop the packets for this node 26. So so it will only send this control messages, not the data packets. So when we looked at the packet drop and the energy usage parameter, in the 3 control trials, so malicious sync processed like 44, like average 40% of the packets, whereas the real non-malicious sync node processed only 60% of the nodes. So it would have processed 100%, but in reality, due to this malicious node, it only processed 60% of the nodes. So that indicates that like packet drop could be used to identify this attack, right? Like selective forwarding attack, sinkhole with selective forwarding attack. Whereas like energy usage was not that much made any difference. So the another attack that was simulated using Kuja simulator is wormhole attack. So basically in this wormhole attack, 2 nodes kind of collude, right, and form a link. Thereby, it kind of dupes the nodes that as if they can do a better job than the other nodes, right, in forwarding the packets. So so by doing this, this attacker can control the routing of the network, and also it allows the like attacker to bypass the router or even the bigger networks. So that we used the concept of directed graph radio medium in the simulator to model this attack, and where we used like nodes 7 and 10 to be used as the malicious nodes that they collude. Right? So basically like using the strong radio signal in the simulator. So in reality, like we can use the powerful simulator for powerful transmitters to simulate this kind of attacks. So when we looked at the effect of packet drop or the energy consumption, there was not much of difference. Like we could not identify any difference like with and without attacks. So so probably like these parameters are not may not be a good indicator for this attack. Like packet loss and energy usage may not be a good indicator for a wormhole attack. So we may come up with find additional parameters, other parameters that would be able to identify this attack. So another possible attack is clone attacks, right? Here a node can be like cloned with malicious intent, right? So so basically like we can copy the logical attributes for a given node, like, which is non-malicious in nature, and the friends or the other nodes in the network will be attracted to this cloned node, which is actually malicious in nature. So to simulate that, so basically like what we did is like we disabled that simulators check for duplicate nodes, and we then actually duplicated a node, right? So basically like the non-malicious node 26 we cloned with another node that with the same address, right? So as a result of this clone net, node, like, so this kind of causes instability among all the other nodes in the network. So when we looked at the packet drop, so that kind of, we could see there is, again, depending on the run, there was change in the number of packets processed, right? So out of 100 packets in the trial one, like we had like 69 packets processed, and in the trial 2, 91. So it's kind of, there's not consistency, right? This could be due to because these two nodes kind of sending different signals, right, to the other nodes. So that could be the reason that there is a difference in the number of packets processed between these different trials. So so basically, like, yes, that's a possible. This could be used as a parameter to identify this kind of attacks, right? Because there is a change in the number of packets processed from the control simulation. So again, there is we could also see the difference in the energy consumption in this attack. So as we could see, like some of the nodes, like that is neighboring to this cloned nodes, right, seems to be doing like more work, right, by measuring this energy consumption. So so we could kind of come to a conclusion that energy usage can be identified as one of the parameters for this clone attacks, as does the packet drop. So the last attack that we simulated is denial of service attacks. So we are here. So basically here, like, as you would know, like the nodes kind of bombard the sink node, right, with packets. So thereby it does a disservice to the other non-malicious nodes, right, the sink node. So this is an important attack because of the resources, like asymmetry in the IoT network, right? So the resources is not that much high to kind of serve all the nodes, like if there is a attacker that kind of uses all the resources. So so this is an important attack, and so there are other approaches that addresses this denial of service attack. So there is kind of some kind of trade-off between the detection rate and the overhead that is being used, that is available to detect the attack. So so to address this issue of overhead, like our motivation is, can we use these simple parameters like packet drop, energy consumption, energy usage to identify, detect, and attack efficiently? So to test this, to simulate this attack, again, like we used so 25 nodes, and where like 24 nodes send 1 packet per minute, whereas the malicious node sends 100 data packets per second, right? So as a result of this, the sink node is bombarded with so many packets from this malicious node during this simulation. And so the results that we saw for this packet drop is like, so out of this, like from non-malicious nodes, like that could have sent like 100 packets without any malicious node, right? Like out of that, like average 92 packets were processed, right? Like if you add like 4 legitimate packets that could have been sent, we could kind of come to a conclusion 96 packets would have been processed. So whereas like out of the 24,000 packets that were sent by the malicious node, only 6%, or roughly about 1,500 packets were processed. So still we can kind of come to a conclusion that packet drop can be used as a parameter to identify denial of service attack. So again, for the energy consumption, again, like there was some difference, there was some change that we could see, right? Like without any attack, the whole network was like kind of performing under like 5% range, right? With this attack, it increased to like 5.5%. And we could see the difference, like especially in the nodes in that path from malicious node to the sink, right? So for example, like the malicious node was in a node, like was identified as node 26, simulated with 26, the node 26, whereas like the path between that was doing a lot of work, 26 to 10 to 6 to 1. So we could identify those nodes are in energy usage is increasing. So we could kind of identify, we could use that as a parameter. So that could be one of the conclusion that we came to. So with these parameters, like for a denial of service attack, we calculated threat index, and with and without attacks, simulated threat models implemented, like the threat index came down. Like once we take action on those nodes, the threat index comes down. So this kind of demonstrates that the important parameters can be used to identify the node and take action, right? And cause then like the system to be stable. So this simulation work I was working with my student, whereas like I'm going to talk about a vulnerability assessment work that I was working with one of the researcher at Honeywell for the aviation systems. So this is more aviation cyber physical systems aspects. So here we looked at vulnerability assessment between the data between the ground networks and the aircraft wireless networks, and also the vulnerability assessment between the software, the cyber system that is used for the flight book and the data loader, right? And so we have different cyber physical systems that has been assessed, right? For example, like the hardwares like network interface controller, the networks, the software that goes with the data loader and the flight book. So we looked at different tools, like is this open servers, test servers, and the test networks, and to assess the vulnerability of the system from attacks as well as from the penetration testing perspective. So that's some of the important tools that we used for the vulnerability assessments are like Nessus to identify the vulnerability of these open test networks and test servers. And also like used penetration test tools like Metasploit and Backtrack to exploit some of the vulnerabilities. For different attacks like denial of service attacks. So this experiment is basically like more from cyber physical systems aspects. So some of the previous preliminary experiments on just on IoT based environment and the cyber physical systems are fairly successful, and so main like my planned future work, like I've been working with Professor Bhargava in this, like involving human aspects to do and also like do like intrusion prevention, and also like fault tolerant replication, or in autonomic having more autonomic features included in this intrusion response and intrusion tolerance. So this and also like there is a good possibility of doing like vulnerability assessment involving not only the cyber factors but also the human factors. So to summarize, we proposed like a holistic framework, right, to mitigate IoT-based cyber physical human systems. Right, like the concept of using, like, can we use identify parameters from different systems, cyber physical and human systems, and use that to detect and respond from attacks. Simulations of common threat models using IoT simulators are fairly successful. However, like having like involving threat modeling involving human factors and human biases, dynamic human involvement is critical, and need the future work will be concentrated towards that. Thank you. Any questions?
So, in the recent Boeing plane, seems like there is some kind of a, not attack, but some failure. And they're trying to say that the pilots are not trained, or they don't have the experience to deal with the problem, because cyber failure is requiring some intervention. So, what kind of attacks and failures can human beings cause? I realize this. The environment, physical environment, gets attacked by the computer, software and hardware attacks. But how can you? What attacks are there for human?
So the thing is, like, there's a possibility we can confuse the rational thinking of the human, right? Like so with cyber aspects, with the physical aspects, because like the human cannot think 100% rational all the time. So there's a possibility that could be exploited by confusing.
So the attack is on the human.
Right, like the human thinking.
Okay.
So again, like, so the thing is, can we model that bias or model that rationality, right? And how we can, what are the parameters that could be kind of used?
So like computers are driving you crazy.
Right.
I mean, that kind of a thing.
Yeah.
I was listening to National Public Radio this morning, or maybe yesterday, and they were talking about in the machine learning, there is a lot of bias.
Right.
And I think that may be something that can be modeled. And they were talking about some psychologists who need to look into it. So,
Sure. I was talking to Professor Karthik this morning. So yeah, we were discussing about that, like how we can, like the machine learning systems are not doing the right thing, right? Like, because it's not trained properly. So again, like, yeah, that's a very important problem, right? How to avoid bias in the machine learning systems. So that is, it's a big problem on its own. Yeah, so future work, like I'm planning to kind of work with Professor Karthik on that.
But bringing the human into the paradigm of, I mean, or in the loop, that makes the problem even more challenging. So I think you are on the right track on cyber, physical, human systems.
Especially like, yeah, with now machine learnings are being kind of used for like even detecting and the responding. Like, so again, like if human is not as susceptibility, the machine learning algorithms are going to have the same issues. So it's yeah, definitely, yeah, as you
It's a very nice
mentioned, like, it's
topic.
a very important problem.
The- oh, I was going to say, the question, in your kind of intrusion, in the intrusion detection or the response, are there things that, signals coming from the human that you involve in that? And I mean, perhaps not explicit, like for example, noting that a human perhaps keeps hitting a button might suggest that there should have been a response and there wasn't, and so that there's something under attack. Are there ways that you explicitly model the human somehow, the human interaction with this system being an identifier of a vulnerability
Sure, like
or of a threat?
So like probably like we could kind of again similar to a machine learning problem, like you can have the data like in a normal situation how the human will perform over a period of time, and like if some kind of attacks are performed against human, like what kind of, how the signals, like what are the signals changes. So maybe can we tap that parameter? That could be an, like, and again, like, so that could be used in the whole system, that kind of identifies the attack or responds to the attack. So I think again, yeah, I think that's a good way to kind of look at, like, can we tap in those signals, like brain-computer interface.
I have one other question. You noted at the end that the CPHS approach identified some vulnerabilities in the aviation systems that had not been others. You may not be able to talk about this, but can you give an example of kind of a vulnerability that was identified using this approach that hadn't been identified previously? Or, what specifically about thinking of it as a CPHS resulted in identifying something that hadn't been previously found? So
like CPS versus CPHS?
Yeah. And what was there something specific, an example of something specific that you were able to detect because
I think
of
as Professor Bhargava mentioned, like kind of confusing the human being.
Yeah. So you actually found some specific examples where you could point to that becoming a problem, or?
Like as like a pilot, right? Like,
yeah.
Like can like instead of doing a direct attack on the physical system or cyber system, can we confuse the pilot itself, because that's more vulnerable than like doing something in the because pilot controls the whole thing.
Well, a cyber attack could make the pilot even more tired and not only confused but stressed, and then behaves differently. And then the response time of a human is much lower than from a cyber solution. So I think somewhere we can model the way the human reacts to problems versus the autonomous cyber system reacts to the problems. One could, be just going ad hoc, by, just guessing what to do, whereas the other one is following some method and algorithm which is confusing the system.
Right. Or can like a machine learning algorithm take place when there is a confusion? Like, can that drive the system?
So what you're saying is the autonomous cyber system could incorporate the human behavior
When there is
to make a better learning model and better
response.
response. Interesting direction of research.
Any other questions? I'd like to thank our speaker, thank Dr. Kumar.
Thank you.